Okay, this time we will talk about 3D vision and learning-based vision, how to solve this problem. I'm going to talk about first stereo matching, then I'm going to also talk about camera relocalization and also 3D pose estimation. Okay, I'm going to start with this algorithm called Monodepth. First of all, let's remember the fact that stereo matching is something similar to optic flow. In fact, 1 degree of freedom less. But here we would like to have a very precise and dense results at the end. Now, the conventional techniques, obviously, you can have a ground truth which is obtained by using some active sensors like LiDARs or whatever. Then you will just regress your disparities or depth values. And based on that, you will try to uh, propagate back your error. That could be one typical way. From some ground truth, you can try to estimate your results. But the interesting point here is uh, this monodepth algorithm basically achieves estimating of the stereo disparities using unsupervised data. Therefore, it does not use any ground truth information. That's very important because you can simply find and use stereo cameras everywhere and you can collect data very easily. And this system, this algorithm, only uses that stereo camera inputs to train their own system without any ground truth. Okay, therefore, our regression estimation of the disparities are only by using appearance matching. Okay, therefore, the correct disparity should match the intensity on the left image with the corresponding pixel on the right, or vice versa. Okay, now the most important problem here is maybe I have to talk about. If you are talking about making an appearance matching using disparities, please note that you have to find the corresponding disparity vector at an integer location here, and you have to go to the next frame and you have to obtain the corresponding disparity, maybe which is in between 4 pixels, and you have to make a bilinear interpolation of the intensities IA, IB, okay, IC, and ID, and then return back and write that value to here. Therefore, this disparity, this D disparity, will be defined on the image where you are trying to synthetically generate an appearance match. Okay, therefore, if you have left image, okay, if you have left image, then you have to, therefore, you have this image here, for example, then you have to have the synthetic image generation on the right, so that from the left, the right could be generated, and by this way, you will be able to compare the synthetic result. Okay, therefore, if you have this input, then if you give this left as an input to your system, then the disparity should be defined on the right. The disparity should generate the right as an estimate using interpolations and bringing back to the right. Then the target, the real ground truth intensities, and the synthetic intensities, which is a function of disparities, will be checked, and propagation of the error to update your D. By the way, please note that we typically again use an hourglass network, just like in optic flow semantic segmentation. Okay, therefore, first semantics is obtained, then we obtain it and we will expand it back. Now, therefore, the most important trick is this naive approach will not create something good, because then you will only have from left estimation of the right. Okay. Another technique could be using left and right together, okay? Then defining your D left, which is estimated at this point. From here, you will estimate during training your synthetic left, hence using synthetic left, the real left, and the difference can be obtained. By the way, I would like to mention one thing more. The name is Monodepth. At the end, I'm gonna use this using mono cameras. That's the whole aim, by the way. There are algorithms in stereo matching like GANet or some others, which are inputting stereo pairs and outputting disparity using neural networks. This is one step further away. It is saying that only I'm gonna use during inference single mono image. During training, I'm going to use stereo matching. Therefore, one trick could be obviously left and right together, and you calculate the D left, and from here, you make your estimation of D left, okay? And in the meantime, you use this one so that at this point, you can estimate. The problem here is, maybe I should also emphasize, I have a left image as an input to a black box. The system is learned to generate right disparity. Oops, there is a shift. I mean, there is a person maybe shifted. Maybe you will make a decision. Therefore, working with left, estimating right is not a good idea. Working with left, estimated left is good by the help of this kind of a strategy, okay? But this doesn't have left-right disparity map consistency, okay? This is meaning no left-right. If you are not also estimating this one and that one together, then you are losing some information. Therefore, from left you calculate right, from right you calculate left. There are two disparities, and those two disparities should also match to each other. Therefore, by taking a pixel at 3, 5 location with the disparity 7, please note that that 7 disparity is a depth, meaning that depth can be projected to the other image, and at that image it will point something, and that there is another disparity on the other image, and those two disparities should be maybe supporting each other, okay? Therefore, there should be a way to check these things, like the directional concepts in optic flow. Hence, during inference, mono images, which is creating two maps. Please note here, you are not only enforcing your single image to create two left and right together. During training, you need this so that you can make a propagation of the error from here, and similarly, this is already available and you can propagate the error here. This is the monodepth architecture. During training, two data is used, but from one of them, only one of them, creates two disparities, and these two disparities are checked for consistency. These two disparities are also trying to make intensity matching, and those disparities should be smooth. Okay, therefore, this is a typical upsampling part here. This is something like this. At any point in the network, first things first, I have the disparity estimates, left and right. I make some inference at every layer. Those are upsampled and put it here. There are two of them, this one and that one. In the meantime, from D left, I generated D right estimate. From D right, I generated D left estimate. And I can now look their consistency, whether these are consistent with each other, okay? Therefore, one disparity generates another disparity, saying that the seen points on the other image should be has this disparity. And obviously, they should also give the synthetic generation. Therefore, in this way, we are obtaining this information, and from this information, through a convolution, we are also generating an upsampled version, and finally here, we could propagate back our appearance errors, disparity consistency errors, disparity smoothness errors. Okay, there are these three errors at the end, and you have to just propagate them back. Okay, this is the convolutional, and this is the upsampling that we are doing here, and these are typical results. Please check without this left-right consistency. Therefore, this is this, and this is this one. Much precise results. Once again, some detailed at some points here, here, or here. The Monodepth is giving much better results in terms of both crispness and maybe the correct results. And more importantly, please note, I am obtaining these things using only a single frame. Okay, this is a little bit not very intuitive, considering the fact that, I mean, you need multiple views to obtain any kind of information about any scene, but this system trains with some kind of data, like autonomous car training data or some other data, and the results are learning based on this thing, and the results are relatively good when you have similar data during inference. Otherwise, slightly dropping of the performance, but still, we could have relatively good results if you have the same scenario. Okay, I'm going to talk about a little bit on the pose, but this is not a real pose estimation. This is camera relocalization problem. Okay, it is called PoseNet. It is trying to find the absolute pose. Absolute pose means rotation and the translation of the camera of the given single image, but from a set of images in the library with known poses. Therefore, with respect to a coordinate system, you have 1,000 images. Then you have a single one unknown, and you try to estimate it. It is an appearance-based localization. Therefore, you basically estimate this. And what we are doing is the 3D position and the 3D orientation, which is represented by a quaternion, is estimated. 6 floating numbers are estimated at the end of the network, and the input image is nothing but your data of the current frame. There is a GoogleNet architecture with softmax layers, with 3D regressors are for these numbers, and the loss function is like that. We have some ground truth. The network is trained like this. You give some data, and from that data, you try to minimize the position and the quaternion, unit quaternion, as a weighted sum of these things are obtained. A typical regressor, okay, image in 6 floating numbers whose ground truths are available, supervised. You have to estimate them. There is an interesting result here. First of all, green is training data. There is a scene, okay, like Metro campus. I don't know where this one is. There is a campus. You move around and you capture those triangles, which are training data. With your GPS and with your camera orientation, you know the ground truths. The greens are ground truth. The greens are the training data. Sorry, whose ground truth information is also available to us. Okay. Now, then we make another walk. We make another walk, a test walk, which is reds. Okay, sorry. This is reds. We make a test walk, and we try to estimate it. That test walk is, the ground truth of the test walk is blue. Therefore, here we are, new data. In the campus, we go around. Now we are moving around once again in a different path, not exactly the same path. The path of the greens are training data. This is your camera. And the blue is relocalized, and you would like, for every green, you know rotation and translation. But you don't know the new one. And the blue is the real locations, the red are their predicted locations. Okay, therefore, for example, these are typical data, which is the test ground truth, which is something you can see in the training set. We have this one, and the estimated pose for this one is equal to this. Similarly here, therefore, this is called camera relocalization, and we are trying to estimate the view once you have a training set with ground truth poses known, and we are estimating our current location with respect to those available data by the help of a network. This is called the PoseNet. Now, how about 3D pose and dense depth together? Therefore, let's think about not only single stereo pairs you are using, but how about estimating the pose of your autonomous vehicle plus the dense depth together? Now, there's an algorithm called SFM, shape from motion learner, okay? And the idea is we are using a warping based image synthesis, and we are estimating the relative pose and dense depth together. Please note, if you have two images, okay, whatever you are moving or not, then the pose between them, if you know it, rotation, translation, if you know any dense depth, then the other intensities could be obtained, and you warp and image synthesize. Now the trick is we will have three monocular frames. Three monocular frames. That's interesting because there is no stereo here. Time, only a monocular camera and time information. And there is a pose CNN, okay, like something like a PoseNet, but this time there is no ground truth poses that you know. The only thing you know is images. And this pose is creating angles and translation. And in the meantime, there is a differentiable image warping, which means you will just estimate the after doing warping, we will differentiate and we will try to propagate the error that we have. Now, first of all, from a point on one image, using K inverse as your camera intrinsic. This is your depth, dense depth from your homogeneous line that is going to infinity. This is creating the point that you have. This is estimated. This will be estimated, by the way. That will be estimated. And then there is a transformation that is also estimated using pose CNN. This estimated using dense depth, and then putting this K, you project to the other one. Therefore, the trick is, if you are trying to have a pixel and you would like to generate this target from source, you make this projection. This projection is this projection, okay? Therefore, then you obtain PS. PS goes in the middle of four intensities. You make a bilinear warping, and then you return it back to here, okay? Therefore, this is your IT target is I cap S. From the synthesis, you obtain this target at the same point. This is the thing that we have talked about a few minutes ago. Okay, then we are using bilinear interpolation. Now let's look at the overall architecture. Three frames, T, T minus 1, T plus 1. There is an object P, okay. For every object, we will do these things. There is a depth CNN, there is a pose CNN. Depth CNN is generating, estimating this one. Okay, dense depth. This is your dense depth. And at the corresponding location, there is an estimate of D. Then this could be projected back through this information. and you will go to another point here and here. Now, this projection obviously requires this translation, okay? And that translation, therefore, this one is estimated from this pose network. And then you can come back. I think it's very trivial. There is one image, it estimates a depth of every pixel. Then these two guys are estimating one pose, these two guys estimating the other pose, and they basically generate the error. Therefore, through these things, I can obtain my errors, and I can find from this image a synthetic version of this, from this image a synthetic version of this. Please note, once you define the dense depth at this t, from t you can obtain to here, and you can get this point back there, and through this you will be able to obtain intensity warping error, and the result, this target view, which is rendered from the source views, and using the predicted depth and the pose, we are warping the source images, okay? And this is the resulting scene, and okay, this is our estimated dense depth, okay? Uh, One important thing to note here is we also estimate pose at every time instant between t and t minus 1 as well. Now, my final algorithm will be Monodepth 2, which is a continuation of Monodepth, which requires stereo. The authors affected from SFMLearner, they say, how about doing all these things using mono algorithm? And again, this is completely unsupervised, okay? And 3D pose estimation. And obviously, 3D pose estimation is not very easy when you have moving objects, by the way, don't forget, because then you are talking about every moving object could have their own 3D pose, okay? And the training is not by stereo, but only monocolor video. Now, during inference, you give a single frame if you would like to estimate disparity, dense disparity, and you give two frames once you would like to obtain the pose between two frames. Therefore, pose CNN requires two inputs, disparity, the depth CNN requires two of them. Now, the trick is three frame appearance loss and the masking. This is the real difference. Once you don't have any relative motion, you would try to ignore those pixels. Let's see how it works. There is a color frame. There is a depth network, as before hourglass, but also we have these FPN, okay, feature pyramid network. And in the meantime, I have this double frame, and pose network is regressing this transformation, rotation, and translation. Now I have dense depth, I have transformation. Now I have three frames, -1, t plus 1. Okay. As you can see, we are moving. For example, there is an occluded pixel. That occluded pixel cannot match to here. Okay, cannot match to here, but it could have a good match with respect to the other one. Therefore, the algorithm is what it's trying to do is it is not trying to average the error. In other words, this error E1 and this error E2, there is a high error, there is a low error, and you are trying to average them for this pixel like here, like 5 plus 1 is 3 kind of. But rather 5 and 1, you choose the minimum one, saying that, hey, I don't believe this, there should be an occluded pixel. I'm looking to the minimum one. If there is a minimum one, that should be an occlusion in the other frame. I shouldn't use that occluded pixel. Okay? Therefore, that's how we basically improve our appearance loss. And we also have this multi-scale depth decoder for obtaining some improved results, okay? And that also improves the typical result. With respect to monodepth, please look to the Monodepth 2. We have much better results compared to here, okay? And these kind of little tricks are basically improving and giving you sufficiently good results. As you can see, I am estimating from mono images not only the dense depth, but also the 3D pose together by only using a mono image sequence.